Okay, so in the first step, we're doing acid-base chemistry with the H- as our base. Why? Well, I like deprotonating alcohols using H- because it's irreversible. Typically, acid-base chemistry is an equilibrium, right? But understand that when you remove the H from an alcohol using NaH, the H- grabs an H, you form hydrogen gas, which bubbles away out of your system. And once it bubbles out of your solution, it can't reverse back. So this is a nice way to effectively make and transfer all of your alcohol into your deprotonated O-. Once done, we're simply going to perform an SN2 to form the benzyl system. There's your SN2. And you'll see it written like this, or you'll see it written like this, especially when the molecules are really big and you're, kind of short on space. Acronyms abound in organic chemistry, and I can provide you a list by in alphabetical order of the most common acronyms so that you can look them up really quickly. For a while, I think during seminars as a grad student, I would have this list of acronyms because people just talk in acronyms, right? It's like rampant, and so you're like, what are they talking about? So you had to really quickly look up that acronym. Okay, well, how do we take it off? I want you to look at the product. Sometimes it's all about perspective. Okay, the perspective we're looking at, we're coming at it from the chapter of how to protect a functional group. I have an alcohol and I want to protect my alcohol. Here is my alcohol protected with that thing. Okay? But now I want you to go back. I want you to go back to your undergrad Orgo 2 days, right? Go back to Orgo 2 when we covered benzene chemistry, aromatic chemistry. There was all of this special chemistry that happened at the benzyl carbon, right? The benzyl carbon is this magic position where stuff happens. It's kind of like an allylic, it's a magical allylic position. It's even better. And we cover this reaction. If you go back in your book, you can actually add hydrogen and say a nickel catalyst and hydrogenate the benzyl position so that you totally eradicate the carbonyl that you had. Go back and look. We did that. And it's because it's at a benzyl position that you're allowed to do so. So if you just turn this molecule around, right, you can see that this carbon right here is a benzyl carbon. So if we can do that on a carbonyl, we can definitely do it on this ether-like system. So removal could be with just hydrogen and some catalyst. Does it have to be nickel? No, there's lots of different ways to remove it, but probably the most prevalent way is hydrogenation. So yeah, you're going to form this hydrogenated benzyl position. But this is now not the thing that you're interested in. This is your byproduct. That's why I say it's all about perspective. In that chapter in Orgo 2, we were all concerned about the aromatic ring. We were doing stuff with the aromatic ring. Our products were going to involve that benzene ring. Well, in this case, that benzyl position can get hydrogenated, reduced, but I'm not interested in that benzyl thing anymore. That's just a throwaway byproduct. I want it to reveal back the alcohol that I had once had. So this alcohol is my product. And so I'm just going to use reductive conditions to afford that. Sometimes though, having a benzyl group is not going to work for you. Why? Well, sometimes you might have incompatibilities with respect to other functional groups on the system. Let's say you had protected your alcohol with a benzyl group, and now you're ready to deprotect it. So you're like, oh, I'll just hydrogenate it with nickel and, H2 gas. The problem is that you'll surely remove the benzyl protecting group, but you'll probably also hydrogenate your double bond, and maybe that's not what you intend to do. Hey, if that's what you intend, you can kill two birds with one stone in one pot, but oftentimes that's not what people are going for. So you have to be very strategic when you're choosing which protecting group to use, and given the future reactions you want to run or the future functionality that you don't want touched. This is where the art of synthesis happens. An option is showing you these slight modifications to functionality. So we talked about the benzyl group. Well, let's take a look over here. If you look, you can see that this is my molecule. This is the goal. I want to take off the protecting group and go back to my alcohol. Okay, so I'm showing you in blue what maps to what. Now it looks like I have a benzyl group, but it's not a benzyl group. It's got one extra functionality on there, and that is this methoxy group at the para position. Thus, this is called a PMB group. A para methoxy benzyl. So it is a benzyl, but it's a paramethoxy benzyl, and that methoxy group makes all the difference. Why? Because I've highlighted it in yellow to show you that both the methoxy group and the CH2 group, that benzyl carbon, those are both electron donating groups, thus making the ring electron rich. The way that we're going to remove the PMB group is using a reagent called DDQ. DDQ stands for 2,3-dihydroxy 5,6-dicyano 1,4-benzoquinone. Ugh, that's a mouthful. Hence we call it DDQ. And some water typically. And what you'll notice in DDQ, I've drawn the molecule here, you'll see that there are a lot of functional groups, one at every carbon of the ring, in fact, that are all electron withdrawing groups, thus making the ring very electron poor. Okay, this is important. This sort of pairing is really important. DDQ is so electron poor that it will entice an electron from the now electron-rich ring into itself. How does it do that? It's going to donate one of its electrons to the carbon I'm showing you. Now, just, look at it from the side view. It almost looks like a 1,4 addition where the nucleophile is just one electron. So I am transferring a single electron from the PMB ring to the DDQ, okay? Hence the term single electron transfer, or SET. So let's just take one molecule at a time. If this one electron moves to the DDQ, that carbon it's moving to already has 8 electrons around it, so it's got to make way. It's going to move its pi bond over and all the way up to the oxygen. We now have it's almost like an enolate, right? it looks like I just did a 1,4 addition at the alpha beta unsaturated carbonyl. And that places the electron. So if you look at this molecule, the DDQ molecule is now a radical anion molecule. That's what it looks like now. All right, what about the PMB group? Well, it donated that electron, so it's going to shift around. The remaining electron and the one next door will combine to form a double bond, and the remaining one goes next to the O-methoxy. This gives us a radical cation. And I like to highlight the important part of the group because that's what I'm trying to free up. Okay, what happens next is probably a series of some proton shifting and, in the medium, because remember, we got water around. So what's going to happen is that the oxygen minus is going to get protonated by some H plus in the system, and the benzyl carbon, remember there's 2 hydrogens there, with a carbonyl or a carbocation next door, we're just going to use the water as the conjugate base, kind of like an E1, right? This is like an E1 here, and this is just acid-base chemistry. Notice that I'm generating H3O plus in the removal of this proton, and so that's the H plus I can use to protonate that other oxygen on the DDQ. So now I am here, protonated, CN, CN, and my all right, now what? Well, we have radicals, 2 radicals. Another single electron transfer can occur. Let's close the deal. Let's take this single electron and pair it up now on the other system. That is going to put me at an anion now. For the DDQ molecule, which is fine. You have an anion on the ring. It's stabilized by all the electron withdrawing groups, so totally fine. My PMB system, carbocation, totally fine. It's stabilized by the electron donating group, the methoxy group. This is working out great. In fact, better yet, I'm going to actually assist this and skip. I'd much rather have the carbocation on an oxygen with an octet than a carbon as the carbocation. I'm sorry, I'd rather have the positive charge on the oxygen because even though it's positive, it has an octet. The carbon as a carbocation is positive and doesn't have an octet, so the more prevalent resonance hybrid is going to be with the oxygen bearing the positive charge. Okay, now what? Water is going to be my nucleophile. I'm gonna make room here. Water is my nucleophile and it's going to attack, aromatizing the ring, and kicking the electrons all the way back up. Here is the group we're trying to free up. There's the methoxy. Draw a nicer arrow here. There we go. And now, what do you notice? What you notice is that you've got this carbon, this benzyl carbon here, and it's got two oxygens, one OH group and one ether type group. This is a hemiacetal. Hemiacetals, as you're aware, are very unstable. Under the conditions, this gets neutralized, and this hemiacetal is going to do a down-out assistance. Proton transfer, right? So the proton that we had on the OH transfers. I'm going to skip this and put it where we want it to go because we want to drive off that group as our alcohol. And we're going to assist down and out. Ultimately, this will give us our desired deprotected alcohol, our goal. But it's also going to give us the aldehyde as a byproduct. So desired deprotected alcohol byproduct. All right, what a crazy reaction. What happens to this DDQ molecule? Well, again, we have protic systems, right? And so you can think about reestablishing aromaticity here. Negative charge kicking in. It's like an enolate. And that enolate gets protonated. That O- can then just get protonated in the system as the OH. So if you look at the DDQ, you started with carbonyls, you ended with alcohols. The DDQ got reduced, right? And that makes sense because in this single electron transfer, the DDQ gained electrons and got reduced, GER. Gained electrons, got reduced. Our P and B group lost electrons and got oxidized, right? We had an ether and it got more oxygen bonds on it, and now it's oxidized to the carbonyl, the aldehyde. So this is a very complex, when you're looking at the whole thing, system, but I'm not going to be testing you on memorizing this. This is just one of those interesting things to know, that you can transfer one electron to an electron poor system and evoke all of this chemistry going on. So if you ever go to a seminar and see SET, it stands for single electron transfer, and this is the type of thing that's going on. It's only going to happen from electron-rich systems to electron-poor systems. You cannot take off a benzyl group using DDQ. You can only do it with PMB. You have to have that methoxy group, that donating group. That makes all the difference.